Thank you to be there. Welcome to the second conference inside the PRELUDE project on educational event series. The lecture conference today is about free running, zero energy buildings and climate correlated solutions. That lecture is part of a long educational event series that started at the beginning of the January 2023, in the 13th of January, where we had the first lecture on proactive forecasting and optimization approaches for intelligent buildings. So mainly devoted to smart building and telecommunication and informatic engineering. The lecture of today is the first of a three-lecture series inside the bigger one that will be treated in between March to June. The topics of low energy building, free running building, and climate correlated design. And in particular, today we will speak about free running, zero energy buildings with a very great sample, and climate correlated solutions. It will be followed by the beginning of May, potentially the 2nd of May, with a short lecture on urban dimension sustainable design with Urbanit Iceland. And will be followed by, again, a small lecture on bioclimatic architecture at different scale with demo buildings inside the PRELUDE projects. And to restart again in the fall season and in the winter season with ICT topics and with advanced digital design topic in the building domain. Also in the other lecture series, all people speaking in the lecture are recognized as experts from scholars, industry, architectural engineering firms. Several of them are PRELUDE partners, plus we have very happy and we are very, and you can say, really acknowledgement and thanks, external people that comes and bring to us their expertise in the discussion. The lecture and the conferences and the workshop are devoted to students, but also to professionals, because we have in parallel in-class people in presence, mainly polytechnical people, but not only, and we have remotely connected people because the link is open. The registration of the meeting will also be made available. Everyone agree? At the end, thanks to the support of UniZEB for the PRELUDE project. Short recap of the project. Now, this series is part of a large European action inside founded inside UH 2020 domain. What we are speaking about is a PRELUDE project, which is, in reality, if you want to decline it with words, is patient building operational, utilizing real-time data for energy dynamic optimization. What does it mean? We are in the advanced smart building topic for Europe. What we try to do and support with 21 partners, several and the majority of them are industry, smart and large industry in Europe, is to support innovative, smart, low-cost solution for intelligent and smart building domain, supporting not only the fact that the building is becoming smart, not only the fact that we're pushing digital twin and other aspects like this one, but also the fact that we support proactive optimization services. Proactive means forecasted. Okay, means that we anticipate the building behavior and we optimize how the building will react to specific stimuli that we expect that will arrive in the next 24 hours, for example. We will support proactive maintenance. We will support proactive building operational optimization for energy and comfort, mainly. Among the other topics, we will treat the minimization of energy uses and the reduction of CO2 emission, and the maximization of self-consumption and supporting renewable energy sources in balance, supporting also a sort of a community-driven visions with the support of our partner. In addition to that, we will develop and support and test improvement in comfort condition control, thanks to the inclusion not only of mechanically driven system, but also of free running building potential. This means that we don't only forecast the energy need, but we also try the fact that the energy needs are minimized in order to allow thermal comfort only when they needed. And when there is the possibility to have free running potential, we will try to take and exploit them as much as possible. The project is supporting and is based on several module development, ICT, informatic models, and others, included in a large digital platform, which is a modular platform for PRELUDE based on the middleware solution PHYSICS provided by MTech Partner. Several of the PRELUDE models based on historical data analysis, but also support not only the analysis of the historical data, but proactive and forecasting of things, including weather, energy, and thermal comfort at different levels of smartness. Clearly, that will be applied to simple residential building, like Italian demo building, and to very complex and advanced building, like intelligent building, small residential houses, like the one that we have as demo building in Denmark, or the living lab that we have in Austria. The event of today, we will see that it focuses on low energy building supporting solution and on climate-correlated vision. We will have three main speakers that will treat with different approaches, with different type of vision and output, this type of support and endpoints. We will see different technologies and different applications, because we have also very, very interesting demo cases, thanks to the University of Padua, that was so kind to present us this very great experience that I hope also all the students here will really appreciate. That support low energy technology, indoor-outdoor correlation, and the fact that we are moving toward zero energy building approaches and development. The speakers are internal and external participants and are recognized as experts. In particular, today we will have these three speeches following my short introduction. The first one is given by Milica Mitrovic and Laura Carnieletto for the University of Padua. It's a very interesting topic. We are very happy that they are so kind to come here, because they present a living lab design and construction experiments that they have conducted with other professors and with a lot of students involved in the University of Padua. It's a multi-year work till now, and I think they will have a lot of work also after in the next year to test and making this great building working. And it is what? It is a living lab that they have developed and we can say designed with students in a multidisciplinary visions, arriving to build it, and now arriving and starting monitoring it, and becoming a place where also people may live for some moments in order to give to them the opportunity to test, optimize, and have an idea of how technology will work. So it's a living lab for zero energy building testing. It's a prototype at present that may host and is hosted where? In the Scuola Edile of Padua. It's very interesting because this project started in 2015. You can imagine how many years it means to design, develop, collect industry, build it, solve all the issues that we may have. You know, we have bureaucracy, but not only that, also the practical things. At present, they have more than 40 companies in the Italian territory involved. So it's very interesting because that supports not only the local, the educational part of this project, but also the fact that students go and work together with industry and with the professionals. So it's very, very interesting to see. The second intervention is led by Zune, which is a postdoc researcher in the University of Brunel in London. She had a PhD in build technology, and she focused on climate change and thermal comfort with low energy and air quality conditions. What she will present today is climate correlation model, which is a work that she has conducted together also with Professor Colocotroni at the Brunel University in developing a simple but very effective, we can say, control logic that helps in choose in between low energy systems, so shading activation, natural ventilation activation, and other aspects like this one, in order to provide thermal comfort in building and indoor air quality by only looking at the external environmental condition, because they produces, and we will see, correlations in between how the building will react and will work under certain outdoor conditions. This makes very simple also to control and imply these things in order to encourage what? The building occupants' decision, the fact that they can self-actuate, so opening window, control the shading, when no advanced systems are in, with a very simple base, because only by monitoring on having forecasted few weather variables, like radiation and temperature, that are variable easy to be forecasted, plus wind eventually, they are able to support how to optimize the building behavior to reach the thermal comfort, indoor air quality comfort, and others. We will see that this realize and support natural ventilation, passive cooling for clearly summer comfort, and indoor air quality. That is helpful and may help us in focuses, also in citizen science approach, to the fact that the people itself, with simple technology, may control and support in a better way their building. The last intervention today will be led by Engineering Fasano and me with the introduction of a new platform that we are developing under multi-project approach. And especially this is what? This is a managing multi-simulation platform that allows to control Energy Plus remotely in an automatic way. Energy Plus is what? It's a dynamic energy simulation tool. So it's a very advanced, we can say, potential platform to, we can say, calculate, predict how a building will react on the energy point of view in a dynamic way. So under early, sub-early weather data. The simulation in itself, the energy dynamic simulation platform they developed, allow to massively simulate parallel conditions and to optimize in between them the one that better react for different purposes. Retrofitting choices, forecasting the next 24-hour event for controlling ventilation and indoor air quality and shading control, but also, for example, supporting the fact of what will arrive under the climate change impact. That's what we will present. Clearly, this is an ongoing action. The other parts of the platform are working. We are testing and implementing it, but especially the climate change dimension is what on which we are working now, and what allows this to connect to a solid simulation platform, multi-weather files, so real-time weather, forecasted weather, but also all the Copernicus database Era 5 lens and the future weather forecasting that support the fact that we can add at geographical level and a single point level the possibility to see how a building or our design choice will react under the climate dimension. So climate not as a fixed variable, but climate as a variable in itself. So 50, 60 past reanalysis data and the future weather file to optimize, for example, insulation level in a specific building or to support policy. So if this is the background, the last things that we only remind before starting the first presentation is that this educational event series is part of a large action that includes also a citizen science activity that is conceived to be student for students in terms of development. So we have in the past year, but also during this year and the next one, involved students, as mainly by the ICT, but also from the architectural domain here, that are developing monitoring kits for low-cost environmental control of systems and schools. The kits will be after passed to high school level in the Piedmont regions to be produced and developed at a large scale in order to allow indoor air quality, thermal comfort, and other monitoring and controlling solution produced by students at low cost, upgraded by students of the high school, and after reproduced by them to be further applied to the world conditions. In addition to that, we have other didactical initiatives like workshop and lecture conference like the one of today. So I thank you very much for your attention, and I now leave the floor to Laura and to Milica.
Good morning to everyone.
Good morning.
Okay, maybe we can start with the presentation of ourselves. So I'm Milica Mitrovic, and I'm a research fellow at the University of Padua. I'm an architectural engineering, but I work with energy engineers, so it's a very strange combination, we can say. I'm part of this project almost from the beginning, from 2015, 16, and actually, I'm a project manager of this project, so I'm following the design part of it and also the construction site. And there is also Laura Carnieletto.
Yes, so thank you for inviting us to this nice event. I have been recently hired by the University of Venice as an assistant professor, but up to one month ago, I was part of the University of Padua as well. I've been one of the founders of the project as well. Since 2015, I just started my master degree actually. So I'm really proud that now we are able to present you almost the final version of the project. So Milica, if you want, I'm an energy engineer, by the way, and I also finished my PhD in energy engineering. So in this project, I basically work mostly on the HVAC system part and also on the monitoring systems of both the envelope and also the systems. So Milica, I think we can start the presentation. So
okay. So everything started in 2015, where most of the world's leaders decided to find out the different solutions for the problems that we can find out on our planet. In the same year, there were some energy students that decided to participate on the international competition of solar decathlon, but in this year they hadn't a know-how how to manage this kind of project, how to manage the team, how to find out different funds to design and construct this kind of prototypes. So they decided to found this laboratory where they can experiment different kind of solutions and to learn how to design and construct this kind of energy efficient buildings. In this way, our vision is about the promotion of environmental, social, and economic sustainability through study, research, and training that are the pillars of our university. And this is explained by three kind of points for our mission. And it is about the innovation in teaching through an experimental learning approach. This means that the students have the possibility to touch with their hands everything that they have the possibility to learn at the university. And the second point is about the innovation in the construction sector through the creation of living lab on zero energy building. For us, the living lab is a building in a real condition. So our first prototype is going to be lived by 3 students. And it's very special because what normally happen, you can have the experiments in the laboratory where you can declare the performance on different technologies. You can simulate different solutions on the softwares, but what happens in real conditions is totally different because you have to combine different technologies in the same condition. In this way, we have the third point that is about the promotion of technology transfer, because we collaborate with the companies that are sponsors of our project. And everything that we are going to study is going to be shared with them. Our team is composed by, we can say, 40 students per year. And they are different. They're structured in different groups. So we have the group of architectural and structural part, the electrical part, sensory measurements, mechanical part for the plants, and the security. And we have also the groups from the complementary part that is about the communication, business administration, and human resources. After the experience that they can have in our project, they can obtain also an open badge that certificate their knowledge, their what they learn basically in this project. And the students are not only the architectural engineers, but we have also civil engineers, environmental engineers, and also energy, electrical, electronical, and so different kind of students. Our board is also composed by more than 10 professors, and they are part of different departments. This is very important because the professors works with us as members, not as professors. So we can learn the practical part of the design of the laboratory that we follow during our studies. And in this way, we can also cover different part of the research. So it is going to be very multidisciplinary, we can see. Our community as a professor, is composed more than 40 companies, and we can consider them also as a part of our team, because they collaborate with us not only for to give us the material that we need in the construction site, but also to design and to find out the solutions that can be combined together. Our project, as I said before, was born in 2015, and we started with a preliminary design. It was very hard because the students hadn't the know-how to manage this kind of project. So we needed different years to finish our executive project. And it happened during the pandemic period. So we started our construction in 2021. And probably we are going to finish the construction of our first prototype in this year. And next year we are going to start with the measurements that we established with the professors and our companies. Basically, the project is about the design and construction of a little house that is about 80 square meters. And the particularity of this design is the co-presence of different solutions in the same conditions. So, for example, we can see on the certain part of the wall, the ventilated wall and the simple wall that is basically we can find out in the normal construction. And also, as you can see on the roof, we have three different solutions. So we have green roof, floating floor, and gray roof. In this way, we can study the different performance of these different combinations. The research areas that we established with our professors are about envelope, internal and external conditions. We are going also to measure the electrical part of the plants, the photovoltaic, the performance of windows, the acoustic part of our building, physical and chemical analysis of wastewater and rainwater, and comfort and productivity. This is very interesting because in our project we have also the psychologists that are going to study how the people can live this kind of smart building from the comfort and the productivity point of view. Most of the time, the people ask us, what is going to happen with UniZEB after the construction of the first prototype and all the research that you are going to do? We can say that after this first phase, we are going to redesign the different technologies and to remonitor different parameters to see the different results from the performance point of view. So it's going to be very interesting. In the meanwhile, we are going to organize different kind of events as a fair or conferences or lectures and something like that to share different knowledge that we constructed during the different years of design and the construction of our prototype. From the architectural point of view, we can say that it's a very simple plan because we have on west a living area with the kitchen and the living room. In the central part of the house, we have the services like data room, technical room, and bathroom. And on the east, we have two bedrooms, single bedroom and a double bedroom. The orientation is south-north, so in this way we can construct the more simple way to monitor different parameters, different solutions in the same condition. And now I'm going to show you our video render of our project. From the construction point of view, the structural part is made by CLT, that are cross-laminated timbers, and in the roof we have laminated beams. It's not a strange combination, and this solution was asked by the company. From the installation point of view, we used stiferite, that is in polyurethane, panels in polyurethane, and we chose different kind of panels because of the finished part. So we can say, for example, on the ventilated wall, we choose the panel fire beam, because in case of fire, there is a combination of different materials that can have a slower reaction of the propagation. And for example, on the roof and the internal part of the house, we choose the panels on GT, that is good in the compression. And class is key. We can say that we can use it in the simple wall. We can say with standard wall with cappotto. We can say in Italian. And we use also different members for the waterproofing on different parts of the house. And it was very special because we understood the differences between different kind of members and also their applications. And it's very important because, for example, at the university, in the most part, the professors say there is a membrane, but you need to understand the different characteristics and their destination in the house. In the roof, as I said before, we have a green roof with sedum, that is a plant that usually is planted on this kind of roof, and it is not necessary to give it water or something like that. So there is also grey roof and also floating floor. We choose these three kinds of roof because we want to understand, for example, what is the performance of photovoltaic, because we expected that there will be more production on the green roof more than on the floating floor in grey roof. For rainwater and wastewater management, we choose to implement the phytodeporation. So we are completely independent from the city management of wastewater, for example. And we have also the tank to accumulate the rainwater and to reuse it for different needs around the house. And there is also the solution for the dispersion of the water that we don't need in the soil. So there is different kind of combinations for this solution. And now I will ask to Laura to continue with the mechanical plans of our house.
Yes, so thank you, Milica, for the presentation. So we have a lot of different HVAC systems inside this building because, first of all, we know that it's a residential building, but we also would like to have it as a lab, both for the students, so for the educational part, and also for the research. There is ground source heat pumps. The probes is 100 meter length, and it's connected to the heat pump, which supplies both a radiant heating system, which provides heating and cooling to the house, and it's also coupled with the mechanical ventilation. The system provides, of course, domestic hot water. It's on the bottom left of the graph. And it's a particular system because we try to use the water both for the radiant ceiling panels and for the mechanical ventilation. And we have a control which is in the collector. And we try to study it with some engineers in order to be sure that we are able to provide the correct temperatures both to the panels and also to the mechanical ventilation. We also have how can I say, we have a particular control on the domestic hot water, but we can see it in the next slide, I guess. No, there is the heat pump one. I'll start with the heat pump. So the heat pump is a commercial system provided by Eneren, which is a company close to Padua. So we try to select also local companies in order to be sustainable also in that sense. The heating power is more or less 7.6 kilowatts, so it's not that small, let's say. And we also have around 9 kilowatt cooling power. The borehole heat exchanger is a W ground source heat loop, and we also we monitor the borehole temperature with an optical fiber, so we are able to know the temperature, the supply and the return temperature from the ground. And we also have a little bit of glycol inside, because in Veneto we can go below 0 during the winter time. It's not that common in the last years, but it may happen. Thus, we decided to be safe from this point of view, and we decided to add it in accordance, of course, with the company. We are able to monitor also the heat pump. The company who is working with us provided all the sensors which are already inside the heat pump, and we will be able to read and collect all the data from the, for example, both from the borehole heat exchanger side and also to the HVAC system side. So we can monitor the supply and return temperature for the domestic hot water, for the ventilation machine, and also for the seeding radiant panels. And I think we can move on to the next slide. So here we have the seeding radiant system. All the modules are actually larger or smaller combination of the green unit that you can see on the top right and also in the corridor. So we have a lot of circuits, as you can see, but we also provided some panels that are not working and some spaces in order to be able to control and check if there is any problem, for example, in the panels, and also in order to be able to install some systems. Because I will present later some sensors that monitor all the envelope. And in this sense, we are able to put some systems in the false ceiling so that we can monitor, for example, what is happening in the false ceiling during the functioning of the radiant systems. The next, please. So, yes, thank you. So here we have the domestic hot water system. You can see here the functional scheme. We may have some, so when we were designing this system, of course, as a designer, we tried to see which were the possible issues that we can find in a normal operation. Since we are hoping that this living lab is inhabited from students in some moments, for example, we may have some periods that will not be inhabited, either because there is no students, because there is the exam session, because we are, for example, changing some layout in the internal part. And we may have some problems, for example, with the Legionella, because we may have like very low temperature between 20 and 45 degrees C, and we may have standing water. Therefore, we decided to put a ring circuit in the bathroom. You can see, I think you can see also from the slide, it's in a light blue. So from the supply side, there are more than one pipe who is living, and we have these ring circuits that allow us to circulate continuously the cold water, so that we don't have standing water, for example, close to the washing machine or from close to the dishwasher, and we are able to ensure that there will be not problem related to Legionella or similar issues, for example. Next one, please. Okay, so here there is the mechanical ventilation system. As some of you may know, usually you provide clean air in spaces, for example, like the living room or the bedrooms, whereas you try to extract air where the air is, for example, a little bit dirty, and it can be from the kitchen or from the bathroom in this case. So in the blue, with the blue lines, you can see there that there are some blue pipes coming and going to the kitchen and also to the bathroom. And the red ones are going to the bedrooms, the single bedroom and the double bedroom, and also to the living room. Although it's an open space, and you may think that there will be, for example, some interference from the supply side and the return side, but we found out that the design was sufficient in order to avoid the interference from the two circuits, and also that it was actually necessary to have these both the supply side and the extraction side there, because the space is quite wide. So it was preferable to have this double solution there. And also, I go back, we have some variable air, water, variable air volume solutions, valves, sorry, that was given by Brofer, which is a company also working with us. This particular system is very useful because it allows us to provide the air from the mechanical ventilation system according to the real necessity of each room. So we don't have a constant airflow, but we can vary according to requests of the room or of the user. Actually, this is also interesting because it's not, since it's a little bit more expensive than, or at least usually in our residential system, we are not supposed to find these solutions. It's slightly more complicated, but it's interesting to be able to study them and to see if there is any, for example, benefit also in terms of energy saving, because if you have a constant volume which doesn't take care of the requirements of each room, you may, for example, consume more energy, and that's what we want to avoid, considering that we are almost zero energy building. We also are able to monitor this system. We have some anemometers inside the canals, the ducts. We will measure the air velocity inside, the temperature and the relative humidity, so that we can check if the values that we are setting in the system is actually the ones that are coming inside the rooms. Of course, this is slightly complicated, the design of the false ceiling, because we have a little bit more ducts inside, and we also need to take care of the noise inside the rooms. Therefore, we're forced to add some silencers and to divide the airflow into smaller ducts instead of one big duct. And that's some issues that in a very small, in an 80 square meter house, you need to take care, because it's quite complicated. You might see that close to the unit in the technical room, there are many ducts going around. So it's something that the designers should take into account. And that's also the importance of working together, energy engineers and civil engineers or architects, because you have to, we are supposed to give to the user solutions that are nice to see, that are convenient from the economic point of view, but also from the energy point of view. And the interaction between different expertise, it's something that is more and more requested also from the company side and from the user side. So can you go on, please, Milica? Okay. So since we are working in university, we are using different tools for energy simulations. The building you can see there has been designed with this SketchUp. And then we provide the simulation both with Energy Plus, as mentioned before by Giacomo, and also with the Transys, which is another dynamic simulation software. In the slide, there is a simple representation of the energy need and also of the outdoor air temperature from the traditional weather file of Venice, actually, because it's very close to Padua, and it could be representative as well. In the Transys model, we also added all the HVAC system inside, so the model was coupled together. And it was very interesting to see the integration, and it was also quite complicated because you have to provide a control to the system according to different values. One of the value can be the user request, so the user need inside the building. You have to provide the comfort, and at the same time, you have to take care of the energy saving of the building as well. And also it was complicated to reproduce the controls that are, for example, already decided by the company, because sometimes the heat pumps and also the radiant panels come with their specific control that you cannot change for some point of view. So we had to reproduce it with the software, and it was quite complicated at the beginning, but now it's working very well. And we were also able to provide a sensitivity analysis. So there is a recent study that we have done with a master student. We try to apply some tools in order to verify the impact of changing different variables, both from the environment side and to the system side, and to see the impact on the energy saving. And I think that this will be very useful in the future in order to determine and evaluate the impact of our actions on the building itself and on the energy consumptions. So can you please go on? Yes, great. So this is a simple scheme of the electrical system. In the bottom part, you can see all the main laws that are connected to the system. And in this case, we are able to monitor also all the electrical consumption of the main domestic appliances. For example, the fridge, the washing machine, the dishwasher, the oven, and all these systems in order to track both the user behavior in terms of, for example, a classical electrical profile, and also to compare the current consumption of the overall house, actually. We also are able to monitor the energy consumption related to the lighting. Each part of the lighting system is a LED, is composed by LED lamps. And of course, it's supplied by the photovoltaic system that I think it's in one of the next slides. So we can move on. Well, before there is the representation of the outdoor facilities. This is the scheme that has been provided by the students, as was mentioned several times before. Each system and each drawing that you are seeing in the slides, it's everything done by students. It has been students considering also PhD students, but mostly from master students. And everything was, of course, checked with the experts in the sector, because the construction of the building followed the traditional bureaucracy that every one of us has to do in order to build up a traditional building. So it's really important to see how students put their effort, because I think that students in the room knows that during their traditional master study, they will not see all the process of the construction phases like this. So it has been very interesting and also very nice to see the results that students were able to provide also for themselves, of course. So next one, please. Okay, here we have all the passages below the floating floor. And you can see how many circuits and cables are coming below. So we have the power circuits, which is the one in pink. And then we have all the data cable and TV cables. And this is important because we have to monitor all the systems, but we should have a very strong network that is able to give the data to the server. And not all of the system are with a Wi-Fi. Some of them are going with cables because it's more safe. So it's quite complex to convey all these cables below the floor. And then we have also the bus for the home automatic system, because it's for example, the windows and other controls are made by the automation system. And similarly, also in the ceiling on the right, you can see all the passages of the cable as well. And although it's slightly less complicated, you can go. Then we have the security system. We have 3 different types of alarm. One is volumetric, and it's mostly on the windows. Then we have the volumetric inside the rooms, and then the magnetic, which is, for example, if you raise the window, it's in the bottom part. I think we can move on as well. Oh, here, okay. So finally, we have the photovoltaic system. As Milica was mentioning before, we have 3 different types of roof, and we will be able to try to measure the performance of this system, controlling the temperature of the roof. Milica was saying before that probably what we expect right now is that the green roof will allow a higher performance of photovoltaic system, and this is because it will probably lower a little bit the temperature on the bottom part, so we avoid the superheating of the bottom part of the panels. On the right side, we will have another, it's only one string because the 2 different roofs can actually be are very similar to each other, so we can extend the analysis to both of them. We are monitoring the temperature on the top of the roof and also on the bottom part. And we will also be able to install the thermoflux meters in order to measure the heat flow going outside and inside from the roof, in order to see the impact of the green roof also on the comfort of the user indoor. And the panels have a 30-degree inclination, because in this particular area we found out that it's the optimal inclination both for the winter season and the summer season. So we are able to install almost 6 kilowatt, which should be enough in order to supply the heat pump and all the other systems. Of course, the user should be conscious of what he's doing. So if we are in summer and we have the highest production, we are supposed to deliver all the electrical loads during the day, or at least we should try, actually. So the next one is the automation system. So here you can see once again the the network between all the different loads. We are using a KNX protocol. We are also using the same protocol for some of the measurement sensor in order to have a unique collection of the data, actually. And the data collected from the sensor, from the heat pumps, and also for example, from the mechanical ventilation, we'll be able to give back a signal in order to control the system, but also they will be able to collect the data in order to be stored and later analyzed from the researcher, for example. We are using also the DALI protocol for the lighting devices. And for the automation, we are using Modbus, but we are trying to let the KNX and Modbus communicate to each other in order to have a unique system to be controlled and to simplify a little bit also the collection of the data. The next, okay. Here is one of the most tricky part of the monitoring system. We would like to provide some hints on the temperature within the envelope. Therefore, during the installation phase, we try to install some temperature sensor exactly on the surface. And this is happening both on the traditional wall, where we have only the thermal insulation, the traditional thermal insulation, and also on the ventilated facade. On the ventilated facade, we are also installing some anemometers, because what we would like to do is trying to measure the velocity of the air inside the cavity. This will allow us also to measure the temperature and the relative humidity, so we can try to see if with all these values we are able to set up a thermal balance and to verify how is the flux and which are the differences between 2 different solutions. We decided to provide a ventilated facade on the south part because we have 2 different uses and we had the sufficient space to install them, actually. So and the south facade is also the one which is more complicated during the summer season. So we are all very curious to see which will be the results of this monitoring system. The next one, okay, so here there is a small scheme of how we decided to set up this monitoring system. We have a very small temperature sensor, which is connected to an Arduino. Every 4th system, we have an Arduino, and then we collect it to the Raspberry for the data, and this is the data signal, so the generation of the signal, and then we are providing it for the acquisition and to the data storage. We are already set up a code in order to collect all this data and to provide a database with all the information. The tricky part here will be to have data which are coming at the same time, and the coherence of this system with also other system of measurement. For example, we are measuring also the indoor conditions in order to estimate the thermal comfort, and as well as the HVAC system plant, as I was mentioning before. So the tricky part we will having coherent data both for the envelope and also for the HVAC systems in order to study the performance of the building at the same time of each component of the building. And this is quite tricky, I must say, because we have the 2 different acquisition systems. One is with the KNX protocol or Modbus, and the other one is with Arduino. So next one. Yeah. Then I give to the floor again to Milica, that's for the life assessment.
Thank you, Laura. I'm going to conclude our presentation showing the last thing that we are trying to do in our project, in our team. So we are going also to analyze what is the impact of our little house, little prototype, and we are going to analyze the period before the construction, so the part where you have to extract the different resources to reelaborate them and to give it to the, for example, to a construction site or different parts of the industry. Then we are going to analyze also the impact of the construction of this house, so during the period of construction site. And then we are going also to analyze what is the impact of the function of our house, so after the construction of it. So, for example, on the left, you can find out a diagram that shares what is the impact of our platform. It is very complicated because we need the informations that came out from the BAUS technical specifications that we can find out in the technical documents, and also we are trying to understand what is the impact of different technologies from the environmental certifications that different companies can give us. And the last part is about the lighting. We studied it with the software of Dialogs, and we studied lighting comfort, illumination comfort, because before this we studied also the acoustic comfort in the house and also thermal comfort, but we understand that also the lighting comfort is very important for the final users of the house. So we developed this with our company, and we are going to use obviously the LED strips and the wheels. And in the last part, I'm going to share with you, show you these photos that testify our purpose versus events, organization of the events. So we organize different kind, principally a fair that is about the education. So in this occasion, you have the possibility to understand our executive project during the tour of the house. And this tour is managed by the professors and the students. There is also a park with our sponsors, and there you can see the solutions, the technologies that they have, and you can understand what is the function, what is their function from the technical point of view. So, for example, when you go to the fair, I don't know, fair of Bologna, there are some commercial people that are trying to sell you different technologies, but in this occasion, we are trying to educate, to transfer the knowledge about different solutions especially to the students. We also organize different lectures at the university with our sponsors. So, for example, you can see the image of the different kind of windows. And this is very special because these technicians share and transfer their knowledge from the technical point of view. So for design in a good way, a smart house, but also how to construct and to use them in the construction site. We also organize the roundtables with special speakers that are very I don't know how to say it, that are specialized in different technologies, and they discuss between them, because these roundtables are very multidisciplinary. So, for example, on the next fair that we are trying to organize, that is going to be on 11th May, we are going to discuss in the morning on the comfort indoor, and in the afternoon we are going to discuss about digital twin and building management system. So it is going to be very interesting because the speakers came from different companies, and they are going to discuss about these topics. So I can conclude my presentation saying that you can follow us on our social media, on Facebook, Instagram, and also LinkedIn, or you can contact us on this mail, or look at our website for the news. Last but not least, I want to share with you 2 videos that explain what means for us collaborate with the companies and to be an active participants on the construction site. I want also to show you a video that we realized during the pandemic period, and it was before the start of our construction site. It was very special because we understand what are the main problems that we can find out during the start of the construction site. So it's only an example, a workshop that we did in 2 months. Okay.
Just a few words on this. So the first is that I think you could see actually the happy faces, although they had the masks. But this is the aim of the project since the beginning. What we felt when we were students is that we were missing something practical, although we were following engineering courses. And we would like to apply actually what we were studying. And this started from the basis. So the learning by doing is the main goal, which is behind this project since the very beginning. And the second part is that we are the place where this house is built at the moment is a high school which is focused on the construction of building. And we also try to teach the construction site safety, which is very important both for the students but also for the companies. And so that's why you were seeing people that had all the safety protection, because we think that this is also what we can get back to the companies which are working with us, and a kind of knowledge we can try to share for the future as well, and for the people who are working in this construction site. So that's an only thing to close the presentation.
Yes, thank you, Laura. If you have any question, we are here to ask for them.
Thank you very much. That's very interesting. We see if you still have questions, 1 or 2. Otherwise, we have at the end we have a question and answer session. In any case, someone will ask you something, because I think that's quite interesting. Someone of you has a question on that? You need time to elaborate? If they need to elaborate, I will ask you something. Okay. The first thing is you have involved a lot of different, we can say, stakeholders, no? And we also have a lot of people here involved, because that's not a typical construction site. Now you have students, a professor, you have a different level of students, because there is also the high school, no, that is involved. Yeah. So
exactly.
Very complex, very interesting. All of them working on the building or building connected, but we also have sociology we have seen, so that's quite a large visions, like we do now in projects. So that's very interesting, this experience. And you also have companies. What do you think is what was the answer by these different type of groups? Because we know now as teacher, as professor, how does it work? Now we know in the real world it works with companies, but how it is for a experience like that, the reaction of students at the beginning at least, and then the end, because that at the end they will be happy. The beginning is more complex. And the reaction, the answer of companies. in the different stage, no? Because now I see you have 40 companies, so it means very positive, the answer at the end. But where the complexity at the more and the easier part for this experience?
Yeah, first of all, we can say that we are trying to follow the approach of integrated design. So we are trying to have the collaboration between different parts from the beginning. We can say that the reaction from the students was very strange because no one of us was able to speak a different language from their side. For example, I'm an architectural engineer, and to understand the part of energy engineers and electrical engineers at the beginning, it was very strange because I didn't know what they were talking about. So, but after a year, we can say that we understand how to manage and what are the needs from different groups, we can say. And from the company's point of view, we can say that at the beginning, they looked at our project as what is this? Can I believe in it? But after we can say 4 or 5 main sponsors, the others came in our project more easily, so we can say. So now there are companies that contact us to become a part of our project. So nowadays it's very easy to find out the sponsor, but at the beginning you can have for example, the professors that believe, first of all, in the project, that believe and work with students. So in this way, you can create more. You can testify the believing of, for example, university in this kind of initiatives, we can say.
What was I think unexpected from the companies is that at the end of the process of the building construction, and also in the communication with us, they started to realize the importance of communicating to each other. Of course, not all of them. There is still someone which is quite not convinced of this, but most of them realize the importance of communicating with different companies, so to try to collaborate to an integrated design, but also how it is important to work with students, because they expect that when they end up at university, they all have the knowledge to start working as other people do, but they realize what is missing in the university and how it is important to try to share the knowledge before the working time.
Because they are the future generation of the professionals, so it's very important to believe in them before they finish the university.
Thank you. Pawan? Yes, we have one question. Please come here.
Hello. At the beginning, you mentioned that you were planning to build affordable project. So my question is, like, is it really affordable now, or it will be affordable in the future? Looking that it's quite individual case and 3 types of roof, different systems. So I'm wondering if it's actually quite cheap or not.
Okay, so from the economic point of view, I think that if we look at it from the it started to be with the main aim to be a living lab. Therefore, the overall cost is actually more expensive than a traditional house. But the general idea is to choose the technologies among the one that we are studying in order to provide an affordable solution in the future. So I think that if we select the proper characteristics, it will be affordable. And also, I don't think we mentioned it before, Milica, but the structure, the layout of the building is actually thought in order to be replicable in some way. So it can be in the future replicable, actually.
Yeah, it's a very simple plan that we designed because of the standards that we need for the metering part. But we can say that this project is very expensive because we are trying to use special technologies for the monitoring, something like that. And for now, our project have the funds about €500,000 so it's not easy to manage all of these funds, we can say. And most of the contracts that we have for the materials are made with the building school, that is high school, where we are going to where we are constructing our first prototype, and the research contracts is made with the university. So yeah, it's not easy to say that this is affordable for the common users and our citizens. But we believe that these technologies in the future is going to be more less expensive, we can say.
That's also a testing lab, no? So you also change the technology. So it's the integration in between things that became very, very interesting also, because after you can have packages replicable at lower cost, clearly, because they became the chosen one.
Yeah.
Okay. You have other questions? Not yet. So I think we can have 10 minutes of pause. Thank you. Thank you very much. And after we come back with Maysoon from Brunel for the second presentation.
So first of all, thank you, David and Giacomo, for organizing this conference, and also those attending the PRELUDE Educational event series. I am Maysoon, and I'm working as a research fellow at the Brunel University, London, and I'm particularly working for the PRELUDE project under the supervision of the Professor Maria Colacotroni. And I hold a PhD in the building technology, and my research is particularly focused and interested in the building performance design, comfort and indoor air quality, climatic adaptation in building design, eco-feedback through the digital technology, and then the building information modeling. Today, from the Brunel University, I will present the indoor environmental prediction using the climate correlation model. So that is mostly for the citizen science approach, because the PRELUDE and focus on the assessing the right level or the manners necessary for any given household, and then provided the optimum tool according to the user need. So our climate correlation model will contribute for these aspects. The methodology, which has been collaborated with other project partners in the PRELUDE, and to meet the PRELUDE innovation and solution, and mainly in the optimizing passive cooling to maintain comfort and indoor air quality. So the performance of the building need to respond to the climate, outdoor climate, and the mass design, relevant thermal envelope, energy efficient building service system, as well as inside even the user, their behavior need to adapt for the necessary changes according to the outdoor climate to keep our comfort and the indoor air quality. So for the user, their behavior and their behavior change model, that is really important for the building performance design. Regarding the behavior change model, which has been developed from the BJ Ford from the Stanford University, it is a very well-known solution. The theory said that the behavior only happens if motivation, ability, and then prompt, they come together at the same movement. So today, the smart home technology and the smart home device, they are helping us for the building energy efficiency and the automation. But the requirements and the saturation, they are vary according to the household requirement. I mean, mostly for the personal related decision from different households. So our research, particularly the climate correlation model, that will be provide a very simplified method that encourage the ability of the user-driven decision-making process in predicting the indoor condition that can be applied. Very simple calculation using the Excel spreadsheet or collaborate with the smart home device. So that is a kind of the concept we have developed. So the study that have been developed and tested for the European country and their climate, and then The study will cover both residential and the office building, but not limited for only this building type. It can be applied for other building type as well. So this map presents the different nature of the climate across the Europe. That is our climate correlation model that need to be adapted for the relevant climate and the local setting for the different building type. So the study, this location mainly for the PRELUDE project, that have the very similar outdoor annual average climate temperature. So we can see the seasonal changes, but also we need to be aware of the seasonal and diurnal temperature variation, and also each location have the very specific cooling degree day and then the heating degree day. So our climate correlation model need to adapt the outdoor climate setting. And then likewise, each location, they have the differences in the solar radiation, daylight hour, wind speed, wind direction. So all those, outdoor climate parameters, these values are vary according to the geographical location. So if we use the climate correlation model, we need to consider their local setting and their geographical location, their outdoor climate requirements. So the psychometric chart, it is very useful during the system design as a modeling design tool to explore the option and investigate system performance under the different conditions. Because the chart show that virtually how it changes, the air goes through, it is heated or cool or mist or humidified or dehumidified. So we need to predict this condition. And then this psychometric study is very easy to explore changes in the control requirements. So here I'm prepared the comparison of the different PRELUDE climate location. So for example, by using the chart to explore changes and load requirements. So for example, for this question, the response to the proposed system can be quickly investigated to see how we can go with the changes under the control element, and the sequencing can start to be developed. So this is the example of the PRELUDE location. I just compare for the outdoor climate varying from the 10 degree, 22 degree to 30 degree. For instance, we need to consider for the aesthetic comfort temperature, which is limited between 10 to 33 roughly. So I just compare for this limitation for the different climate context. So the indoor condition, when we predict that one, and then we need to consider what are affected by the way how the occupant use our building, the building develop, or building envelope design itself, and then how we install service system and how we use it for the energy building, heating, cooling, ventilation, lighting. So all those we need to consider in our indoor condition prediction, because altogether they define the way the building can maintain the comfort and the indoor air quality according to the outdoor climate. So this is the hypothetical because for this this is the factor we need to consider in the developing the climate correlation model. For our study, we have used BSEN 16798 for the building schedule to start our study, because we need to develop our building operation according to the way we will operate the building. So that is the reference, but actually, our climate correlation model, we can apply any customized schedule, whatever we need. But for us, to easily everybody to understand, we just use the BSEN code. So it is the very simple step we started. So this is the hypothetical flowchart for the indoor prediction process. Firstly, the correlation model will develop using the historical weather data and then relevant building boundary condition. So using the prediction equation, the user are able to predict the indoor condition. It is important to stress that the user decision-making process should be considered for the different conditions. For instance, If the windows are closed and then shaded, it means the daylight illuminant for the daylighting could be reduced, as well as the air change from the ventilation will be very minimal. But if we consider for the mechanical ventilation, we also need to aware of the noise coming from the fan that could affect our acoustic comfort. And then while the shading is off and then the window is open, we invite the natural ventilation. So it means we have the very higher air change rate, but also the effect during the winter, our heating demand increase. So we need to consider all those constraints together. So in our climate correlation model, we try to provide a suggestion to review what is the limitation, how we work together, what is our optimum comfort, and then what is the required indoor air quality. So we predicted the indoor environmental condition. First of all, we start with the temperature. So we predict the indoor operated temperature by correlating outdoor climate, especially for the driver temperature. So to do so, we have to define, first of all, the different scenarios that affect our thermal boundary where we're going to predict the run. So for this, we need to consider how we use the window HVAC system that include the heating, cooling, ventilation, and also occupant activity that affect our internet gate, how we use our cooking, cleaning, all those things that affect the building operation. So we have to consider and predefine the boundary condition, and then we develop the correlation chart. So here, the left chart, it is the heating during the office hour, high internet heat gain, high occupancy density, window closed at the time. That is the reference from the one of the our study for the 18th. So this left chart that show the higher indoor temperature if the room have the higher internet gain and then the window is closed. So that is the very office setting relevant correlation model. And then the right chart that show how the indoor temperature it vary according to the outdoor climate. When we have defined the heating, it is around 20 degrees set point temperature in the room, and then the room have the very low occupancy density. So because of the boundary condition different, we can see the different profile of the indoor-outdoor correlation. So that is the example of the climate correlation model, and then the profile for the temperature. For the indoor temperature prediction, we predicted from the climate correlation model. At the same time, we need to evaluate our result. So we are using the adaptive thermal comfort equation. So it means above the acceptable limit, we need the active cooling. Below the acceptable limit, we cannot use the adaptive comfort temperature. So we need to consider active heating. So one will argue that the natural ventilation to be applied when the outdoor running temperature is very low. So it means we need a higher energy demand. So opening window at a time, it could increase the energy demand. So we need to consider how we solve this issue. So what is the alternative for the ventilation? For instance, we can use the structural ventilation or very minimal requirements for the mechanical ventilation, especially to remove some of our indoor pollutant, especially for the CO2 concentration. So all those we need to consider when we start using the prediction for the comfort temperature. And we predicted the air change for the ventilation from two parameters. The first one is the wind speed, which is we use as a predictor when the windows are closed in the room. So it means there is no wind force wind driven ventilation. If we use the window opening, we invite the natural ventilation. In this case, we need to consider the temperature difference between the indoor and outdoor. That can be we can use as a predictor to predict the air change rate. So we need to stress that using this ventilation prediction, that is very important to consider what is the ventilation mode, because according to the single-sided ventilation, the cross ventilation or step effect ventilation, our prediction for the ventilation curve, the strength of the correlation, it can be affected. So we need to consider all those parameters as well. We are predicting the air change rate from the ventilation. We got the air change parameter. So, but the indoor air quality, we cannot use directly the air change parameter. We need to assess the indoor pollutant concentration. So, we are using the indoor air quality to evaluate using the single mass balance equation and the specific CO2 concentration calculation. So this simple calculation, the evaluation is the very common method because the calculation or the equation involve only the air change, the outdoor concentration, and then the characteristic of the occupant that produce the CO2 concentration. So there is the very simple calculation and the evaluation method we can apply, and then we can evaluate it for the required ventilation. So unlike the temperature and ventilation, daylight, it is mainly influenced by the solar time, its geographical location, the orientation of the building, the window, overshading effect from the neighbor building, the run side, the window glazing property, many etc. So all those information we need to consider in our daylight correlation, particularly for the sun relationship, because time of the day, for the different hour, that is really affect for the daylight calculation. So the previous model for all weather sky model, they use the outdoor solar radiation and then dew point temperature value to calculate at the daylight illuminate in the room in the defined boundary condition. So we are using this equation in our simulation, and then this method, from using this method, we can correlate outdoor solar radiation and the indoor illuminant value of the defined scenario. And our correlation is we need to produce by different hour. Let's say for the solar hour, the daylight start around 4-5 a.m. during the summer, or maybe a little bit late around 7-9 a.m. during the winter. So we need to calculate according to the solar hour as well. And then this is the estimate of the comparative study we presented in the K conference in 2022. And then here we compare the climate of 18, which has the Mediterranean subtropical climate and dry and hot summer. And then we compare this climate with Rhine from Denmark, and then which has a Nordic temperate climate, and then fairly humid, and then warm summer. So very contrast climate. We are trying to work as a comparative study using the climate correlation model. And then we use a Plato model, and then in that model, we consider the model have the articulate system with the set point temperature around 20 degrees Celsius, and then window open for 2 hours daily, and then heating is applied during the day, and then heating turned off during the night when the occupants sleep, but the heating turned off when the window open. So it means we are trying to reduce the energy consumption when we are opening the window. So here we can see the predicted temperature for the indoor, that is within the adaptive thermal comfort temperature limit. But also we need to recognize how it happened during the window opening time. So here around the 10 to 18 time, we can see the temperature a little bit drop because we opened the window for 2 hours at a time. So even though the outdoor temperature are different during the summer and winter, our temperature prediction we can see and we can find it is within adaptive limit as well. And then it is important to note that the temperature outdoor, we are using the predicted outdoor temperature, we are not using any historical weather data. So here is the CO2 concentration that is coming from the single mass balance equation, but the prediction for the air change is coming from the correlation between wind speed and the correlation between temperature difference between outdoor and indoor. So the CO2 concentration, we can see that it reduces when the windows are open, the occupant density decreases. And then also we need to know that the window were closed. In this case, the indoor CO2 concentration will be very high, but here it didn't show. But we also need to understand that because of the occupant density, it mainly coming generating the pollutant concentration for the CO2. So that will affect as well. So occupant behavior and then the presence of the occupant we need to consider in the indoor air quality evolution. So this study, this is another example of the black box study, and then we tested the impact of the orientation and then the use of the window opening schedule. And then for this case, we used the Krakow from the Poland. It is a case study location, and the Krakow is a very heat dominant city, and then it has the significant seasonal variation in wind speed. So we need to consider all the outdoor climate conditions when we start developing the climate correlation model. And then in this case, we consider different window opening time. Let's say 2 hour window open during the morning and evening, have an hour open, 15-minute opening time, etc. And then we even try to see we open the window morning only, or we only open the window during the evening only. So we try to find different variation in the window opening, as well as we also consider the different occupancy pattern, especially that affect indoor CO2 concentration. So this is the example of the temperature and the ventilation correlation. And then here we separated the correlation model for the window opening hour and the window close hour. The reason is we are using the wind speed for the correlation for the window close hour, and then we are using the indoor temperature difference between indoor and outdoor. So that is we are using for the window opening hour. So we need to develop the correlation model, correlation equation according to the boundary condition, and then the way the indoor and outdoor parameter correlated each other. So this is the example of the table we are using for the prediction equation. So this table compare how the indoor air temperature, air change, indoor CO2 concentration that could be vary according to the different scenario we define. And that it is really important to know that we are using the focused outdoor climate data in this prediction. So it means when we know the outdoor temperature or wind speed or solar radiation for the next day, we just put those information in this table, and then our result at the other right side, the indoor condition that will be predicted for us. So that is the very simple calculation, and then we can use using the Excel spreadsheet as well. And then after we have tested the climate correlation model using the black box model, and then now we are testing their applicability in the real world model. So we tested that correlation model using the living let from the Pinkerfield from the Austria, and then the technical implementation we follow using the calibrated model. And then thank you, Giacomo, from the POLITO for the calibrated model sharing us. And then here we do have the one selected run, and then we try to demonstrate the implementation process. So it demonstrated the building envelope data, integration of the occupancy information, building operation for the building heating and cooling, and the operation for the window opening time, etc. All those parameters are really important in creating indoor-outdoor correlation model for one specific location. And so using that is only for the testing for the one period. Here I was trying to understand how we can predict for the summertime, but now we still developing for the prediction for the different window opening scenario and then different season. That is currently working in the PRELUDE project. So using the climate correlation model, we are trying to demonstrate in the real world setting as well. So here is the PRELUDE demo office building located in the Krakow in Poland. And then here we demonstrate how to use the correlation equation in predicting the indoor operated condition. So that is the example study. And then we predicted the indoor temperature for the thermal comfort and the aging for the required ventilation for indoor air quality. And we try to provide a comparative study in indoor condition prediction for the current condition and then retrofit case. So that the study is like how we can use the climate correlation model for the retrofitting, what kind of result we can expect. So that is the aim of the study we are implementing in the office building. So the boundary condition, especially for the base case and then retrofit case, they are different. So because of the boundary condition difference, the climate correlation is also different. The prediction equation is also different. So here we can see how the indoor condition will be changed if the office is retrofitted. So this finding that informs us what we can expect the retrofitted action in the typical and the extreme summer and winter day. So based on this result, we can find what is the most appropriate retrofitting strategy as well. So another case study that is developing in the 18 apartment. The apartment have the 3 single room and then 3 twin room for the different orientation. And then here we consider how the different window opening and then the use of the mechanical ventilation, the use of the heating, especially cooling, because it didn't have a little bit warm summer, not warm summer, quite hot summer compared to other European climate. So we have the different boundary condition building service system we consider in this project as well. So this result informed the higher indoor temperature and then higher indoor CO2 concentration we need to expect if we close the window, if we have the higher occupancy density in different rooms. And also the temperature will be dropped and then the CO2 concentration will be dropped if we open the window as well. So that is the example study for the different season for the summertime and then for the winter time for the different room. Because the single room they have the only 1 occupant and then the twin room they have the 2 occupants. So because of the occupant behavior different, we can expect slightly different value in the result as well. So in summary, we started our study using the historical weather data and then we defined the relevant boundary condition for the different scenario, and then we developed the climate correlation model according to the defined KPI for the indoor-outdoor correlation, and then we evaluated our correlation and prediction result using the aesthetic comfort model and the indoor air quality threshold and then the specific ventilation dose calculation and then the CO2 concentration calculation as well. So finally, the prediction process we are using the focused weather data, focused occupancy data, and then focused pollutant generation time. So that is the very simple approach we have developed as well. So meanwhile, we are using the 24-hour prediction result based on the Excel spreadsheet that includes the forecast outdoor temperature, wind speed, solar radiation. That is the three main outdoor climate KPI we are using. And then also the user, they need to feel the indoor condition, particularly how many occupants they will have, what kind of the present, let's say the occupant will be in the room around maybe 7 p.m. to the next day or the whole day, etc. We need to include in this data, and then what kind of window operation activity we are going to do. Let's say we are going to open 1 hour or 2 hours. So there is some information that the user they need to fill in the Excel spreadsheet. So that is currently very simple Excel spreadsheet, and also we are very eager to develop. If someone interested in developing application or software using the climate correlation model, we are very happy to collaborate as well. So that is how we develop the climate correlation model. So that is about our work for the PRELUDE project, and I'm very happy to discuss if you have any question. And then thank you again, Giacomo and David, for arranging this event and this conference. Thank you so much.
Thank you, May.
Thank you.
If you agree, we do our presentation, and after we collect the question for both.
Yes.
Okay, thank you. What we will see is a presentation, the last one of today, that will be about presenting some of the current outcomes that we are working on to develop a platform that support dynamic energy simulation of building with easy inputting and outputting modification for sensitivity analysis. We will see, especially in general, an introduction to the platform, but especially we will focus on the application and the use of this platform for supporting geoclimatic studies and potentially analyze the impact of climate change on the built environment. The three challenges they will support, mainly they will try to face on this specific application, are the fact that passive cooling system and low energy bioclimatic technology are, as several of you know, very local specific. If for the passive heating point of view is the position in some way of the intervention side, they give to us the potential access to solar radiation intensity and clearly the submicroclimate and obstacle. On the passive cooling point of view, things are more complicated. So it means that people in a location that are with similar geographical climate or coordinates may have very different potential for direct evaporative cooling, air-to-air heat exchanger potential, or why not ventilative cooling. So the control and the application of this technology and all technology connected to this type of bioclimatic visions are and requires a lot of specific and focused studies to define how to and where control and apply them. In addition to that, it's quite evident that incentivizing this type of strategies is not so easy and not so diffuse, because it's easier to support incentives for low energy systems because they are mechanically driven and controlled than support incentive for this type of technologies. But it's clearly needed the fact that some municipalities and regional bodies, for example, like some of our partners, are interested in the topic, but they need tools. So something that can support them to analyze and understand how can be calculated and defined the local applicability of this technology, and how to implement according to different design and operational aspects of them, and also to analyze their exploitation when they are in line and when they are connected to a building. The third challenge we will see is the fact that climate change in general requires an attentive vision and a re-engineering of the way in which we think about the optimization, for example, of building envelope or building low energy technology integration, because we generally plan and design on the bioclimatic point of view using typical weather file, but we now know that typical weather files are not so typical, okay? If, for example, in Italy, we refer to the Gianni De Giorgio database, on which several APU files that you can find in Energy Plus, for example, free databases, they are based on 50, 60s. So they are 50, 67 or more years old. If you look at the EWEC file, they are 20 years old about. And if you look at the CTI databases, with a lot or less in terms of variables and potential application in terms of number of locations, they have already 5, 6, 10 years. So what does it mean? That climate changes are impacting and will impact a lot our design choice. If you optimize of a climate of the 50s, we clearly are not choosing the correct insulation panel. And that's also evident in several of our regulations, in which we have fixed a minimal U value that include heating needs and not the cooling domain. Okay? So what we are looking is potential development of tools and support that show these things, that analyze this aspect, and take into account databases that exist, like Copernicus, ERA5, and climate change in general forecasted models that are not usable by architects right now, without a lot of complexity, without a large multidisciplinary proof, because they are, for example, exposing net CDF4 extension that I'm sure we cannot read. Okay? So this presentation do what? Introduce a geo-climatic approach to building design and potential KPIs. That's something that we're already developing in the past 10, 12 years. We present a new tools, which is what we are working on now, which is called PREDICE, that manage massive energy plus simulation and can integrate together climate analysis without building, climate analysis with building, and their integration. And show preliminary application sample for map the geoclimatic applicability of ventilated cooling in Italian climate, and introduce what will be the next steps in the next 6, 12 months of projects. We clearly know, and I hope everyone who has know, that the general context in where we live is a context in which building sector is impacting on the energy primary requirement for 40, 42, 43% globally, and that we are in a world in which the cooling loads are growing, okay? On the market point of view, we see growth of plus 70% of the total market only in emerging countries in terms of air conditioning system installed in 5 years. Okay? And if you look at current and recent databases on industrial panels and industry body in general that works on air conditioning, you see that this trend is confirmed yet. So we are consuming a lot for cooling, we're installing a lot of cooling machine, and it's expected that Europe, in between 2050 and 2100, the cooling load will overpass the heating load in the building sector. So it's not a specific application of the thing in itself, but require this integration in between things. And so for doing these things, to massively change the input of the building, the control system, and the climate, is clearly needed to have the possibility to manage this type of simulation on a large scale. And we work on dynamic simulation because, as just mentioned before, the passive solution for cooling are dynamically, works at least in 24 hours or 7-day even behavior, because we activate the building masses, are not only in immediate response. So, if you maintain this logic in the flow, we will introduce some few approaches that define this climate vision of KPIs. After, we will see some sample of building connected KPIs in which the technology itself is connected to the building. So if we select a list, or we may develop tools or potential solution for low energy or passive cooling system or elements like this one in a building, it's also possible and required to develop in this case the specific key performance indicators that are technology driven, okay? They're connected to each technology. For example, evaporative cooling, the applicability is based on the wet bulb pressure, on the local wet bulb pressure, without pre-treating on the humidity point of view the air. The ground cooling of heating, we are speaking about air-to-air heat exchangers, so low enthalpy horizontal tubes with air, for example. It's clear that if we don't activate the soil in a specific way, the air potential is based on the soil temperature around the tube, okay, which is given by the density, by the thermal property of the soil, and by the depth, and other variables. On the ventilated cooling point of view, it's clearly the heat sinks that we use is the external air, is the outdoor air, if we don't pre-treat it. So that's the variable that we need to take into account. But clearly, we can also start virtualizing the fact that if this is the heat sinks, we also have some sort of design choices. For example, the effectiveness of an evaporative tower is based on the design of the tower itself, on the type of nozzle that we chose, another aspect that we take into account into specific equations that support the key performance indicator. So first of all, we have developed and identified in literature and validated, and when not given, we have developed a new one, a series of indicators that works called climate level. Climate level means that I do not have a building. Eventually, I have a virtual building condition to support the analysis, but I have climate, so temperature, radiation, relative humidity, and all of these aspects. That can be a typical climate, for example, for different period, okay? And that allows us to define the geoclimatic applicability of technology. How much a technology may support me in my eventually building, for cooling the building itself, for dissipate the heat, etc. This was done for several aspects, for ventilative cooling, ground cooling, evaporative cooling, radiative cooling, and so on, supporting, for example, series of indicators like the one here presented in the graph, which is what? Based on local weather, we morph the cooling degree hours. I don't know if you know, degree hours is a sum, okay? The cumulative sum of the difference between an expected base temperature of my building over which I have discomfort, okay, and the external temperature. It's a sort for heating and cooling is recognized, mainly for heating, but it's recognized to be linearly correlating with the energy need of your building, okay? So that's the fact. We can morph the cooling degree day point of view, cooling degree hour point of view to what putting inside the effect that a passive system would have on the airflow, for example. On the building point of view, again, we have developed and supported a list of other indicators that support the integration of the effect of this specific system, evaporative cooling, ventilative cooling, shading activation, and so on the building point of view. That's allowed to define the applicability of this technology in exploiting their potential, reducing the cooling needs or the heating needs when these needs are present, so when we have a mechanical system coupled with the building. But we can also analyze the effect of this technology on a free-running building, so when the system is off, of not present, like, for example, in the traditional Mediterranean house, in which we do not have at least a mechanical cooling system, ventilative system. That's allowed to analyze what? The number of hours, or discomfort hour, that we expect in discomfort, that may be turned into comfort by applying the specific technology with a given constraint of operation. That support the ability to analyze this aspect. Clearly, we need sensitivity analysis. That means to change the input, the design of the building, the control solution for the technology, and so on, in order to identify optimal conditions or control rules. In addition to that, also this allows to analyze where this technology may be applied, may be exploited, or can be incentivized, and how the local architects may, starting by early design, start thinking, okay, that's a technology that I may be interested in applying. There is nothing worse to see a building, like passive houses, that I say because there are examples for that, building, I don't know, in the Mediterranean climate using North Europe standards, okay? We are creating an event, okay? We're creating a very overheated buildings in which we need to use a drastic cooling massive system. So that's not what we want. We need to have local specific technology with simple solutions. If this is the approach, we clearly need tools and methodology to do this. And the tools need to be massive simulative tools able to control dynamically buildings or different type of building, changing all the way in which the building is done and parametrically analyzing its impact.
So now we will present you the PRELUDE platform on which we have been working on in the last mainly 2 years. Also through an example, and then focusing on the ongoing main ongoing tasks. The main purpose of the PRELUDE platform is to answer the EDICE and PRELUDE European projects goals, mainly easing and making possible several kinds of analysis and actions, such as climate change resilience studies, or geographical analysis of different passive technologies potential, which are the main ongoing tasks for now. But in the last 2 years, we have also addressed several other purposes which are already more structured. For example, to support model calibration, or Paolo has worked in the 24-hour forecasting of best free-running building setup for the next day. And we have also worked on scenarios focused on the performance gap analysis between monitored behavior of buildings and simulated under standard conditions. So many different usage scenarios, but what makes possible the development of such different cases is the structure of the platform itself, which is highly flexible, scalable, and modular. Particularly, as you can see from this slide, the platform is composed by 3 main modules, which are the IDF editor, the runner module, and the KPIs calculator module. The IDF editor and the runner modules allow to handle the bindle model in order to be run inside Energy Plus, the software we have already talked a bit today, with automatic and parametric actions on both building construction and operational elements. Instead, the KPIs calculator module allows to compute a great number of indicators, according also to the most recently updated European norms, on both simulation results, but also, and this is the maybe most innovative part, on structured monitored data collected from sensors on the field or from weather stations. The combination of the functionalities of all these modules allow to develop these different usage scenarios for different purposes. Moreover, the platform is equipped with additional modules which allow to manage specific tasks and data formats, such as the APW compiler, which is devoted to handle and translate weather data to the data format needed for simulation, which is the APW format. To conclude, you can see that all these modules are inserted in this gray box. And this means that all this complexity is hidden to a potential user of the platform, which may just need to select the scenario he desires to use and manage a few needed inputs. Then the platform will do all its computation and finally output results in a standardized format. Maybe now we can go on. Yeah, and for now we will leave all these technical aspects behind and focus on today's topic through an example of use of the platform from a recent work we have done with the goal of having a deeper look at ventilative cooling potential in Italian climate. Okay, why is this topic interesting? As you know, there is, Giacomo already told before, there is a drastic growth in cooling needs in Southern Europe, but at the same time, we have highly ambitious decarbonization goals. So passive technologies for maintaining indoor comfort, both in summer but also in the winter time, are of great importance today. However, passive cooling technologies' potential, such as ventilative cooling, is strongly dependent on the specific local characteristics concerning both the weather but also the soil composition. And this inhomogeneity has made more difficult through the years the valorization of these approaches through regulation. So we can say there is the need of ease the access to a global view of the phenomena, for example, focusing on the Italian national scale. In this work, PRELUDE functionalities were used to allow the computation of several climate and building-related KPIs on the typical meteorological yearly weather conditions of all the about 8,000 Italian municipalities. So, as an example of the climate indicators that we have considered in this study, in this work, here there are listed the cooling degree day, which actually can be defined with several formulas, but however it has the meaning of estimating the local need for cooling based on outdoor temperature trend. Then we have the climate cooling potential, which allow to estimate the potential for nighttime ventilative cooling, which is mainly useful for those buildings which are unoccupied during night, for example, offices or schools. And finally, we have the heat dissipation cooling potential, which expresses in terms of watt per hour, the ventilative cooling, yeah, the ventilative dissipative potential. But here you can see a visual representation of some of these indicators and the obtained results on the Italian territory. For example, looking at the first map, you may notice that locations near to Rome and Milan, I don't know if maybe you can, okay, there is Milan and Rome, locations near to there, which are the two most populated Italian cities, are interested by higher values of these indicators, which, as we said before, estimates the local need for cooling. This is in line with the expected impact of urban heat island conditions, and also can underline the potential of looking specifically at the potential of these zones. Instead, in the second map, for example, focusing on the climate cooling potential, we can see that except for the Alps region, the mountain region, in Italy there is a very low ventilative cooling potential during night due to high external temperatures. And this analysis was done looking at the typical conditions, which, as Giacomo said, was based on maybe 15, 20 years ago, weather standard weather files. So nowadays, and looking at future trends, the potential can be even worse. Okay, so our tool, moreover of calculating all these indicators, can also be used to study possible correlations among the different KPIs. And this may result useful, for example, in case some information are missing. So from one indicator, you can derive another one. Besides climate-related KPIs, the tool can also handle simulations, because climate-related KPIs do not need simulation in order to be computed. But we can also handle simulations and compute building-related KPIs. And here you can see some easy examples. For example, just the energy consumption for the energy need for cooling, or thermal comfort indicators that can be defined both for mechanically driven and for free-running buildings. And in the middle, you can see the cooling internal degree hours, which defines the cumulative intensity of discomfort, considering the difference between the indoor reached temperature and the outdoor one above defined thresholds. Here we can see a visual representation also of these indicators. For example, in the maps, there is the energy need for cooling, and increasing in the three maps a fixed rate of natural ventilation in the building. You can see that increasing the ventilation allows to more than half the local need for cooling in Italy. And then there is also an example of a correlation between these building-related indicators, for example, the consumption, with below there is the consumption, with the previously described climate-related indicators. Now maybe we can go on with the platform. I don't know if you want to add something. Okay. So coming back to our tool, it actually allows to compute a lot more indicators than those described so far. For example, the energy signature, which is a very well-known indicator that relates the energy needs for both heating and cooling to outdoor conditions. That can be just the outdoor temperature, but also the solar irradiation. Or we can have the adaptive comfort model. Here you can see an example of an hourly distribution of this indicator. But also the tool allows to handle some passive technologies, such as the earth-to-air heat exchanger of the evaporative cooling units inside the building model in a parametric and automatic way. And this is a big plus of the tool because nowadays these technologies are still partially unavailable to be handled through the main CAD interfaces. So it was a missing point on the market. Okay, but among the main next steps we are now working on, there is a deep update of this parallel module, which is the APW compiler module. As we saw at the beginning, this module is useful to translate weather data that came from different sources, that can be weather station or also web services, in the correct format for the simulation. So the next step will be to accept as the input data source data coming from the Copernicus database. The Copernicus database is an open climate database promoted at a European level, which actually contains a lot of different databases with data related to weather and climate in several aspects, from soil to water conditions and also the classical sky conditions, of data of the past 50 years to the present, with very high and temporal, spatial and temporal resolutions that is reached through modeling whenever direct sources were missing. And the database also contains modeling for future trends based on many typologies of models. So we can go on. In this database, data come in the NetCDF4 format, which is a format widely used for database of big dimensions, mainly considering the dimensional levels, because you have to consider that one file of this database contains points for all European coordinates at like a 10 kilometers resolution, all the temporal scale from 50 years ago to now, all the variables. So very complex file format. So what we are doing is, first of all, an exploration of all the available data, which are a lot, in order to understand what we need for our purposes and to run a simulation, and then extract from these files all the variables we need and translate it to the APW data format, which is not so easy to be built from zero, especially considering its headers part. But as for the PREDICE platform also, all this work is done on the background, is hidden to a final user of the services we want to provide, because the final goal is to provide to any external user potentially, for example, through a web service, the possibility of requesting different sets of weather files to run simulations. For example, if we focus on a specific location, we could ask for a temporal trend, or if we focus on a wider geographical area, we can focus on a specific time period. So these typologies of analysis.
Thank you. Okay, so to summarize and conclude, that in 1 year we can say the tool will be able to integrate this climate analysis point of view. So we will allow to analyze multiple hair behavior on a specific building or technology approach about climate and building integrated climate level. This support, for example, the optimization of building design, support the optimization of technology design, and support also to, in some way, take into account in retrofitting scenario and in sensitivity analysis the climate dimension, but also to analyze the impact of specific operational choices in the long term. It allows mapping the applicability of the different technologies, supporting policy of this type of approach, allows supporting not only the policy, but also architects in early design, in understanding and choosing a correct list of technology, low energy technology for the specific site or at least local climate. And also we are expected to include some urban warfare analysis like urban weather generator from MIT and others to support a sort of small downscaling, clearly to be after upgraded with other tools. In order to have, with easy point of view, the possibility to analyze and run maps of applicability and variation of applicability after different climate change scenario like the one that are shown there for the America point of view. So on this point of view, I thank you. And if you have questions and elements, I think now is the time to start discussing that. We can keep also for May and also for the fantastic presentation on UniZEB. So if you still have questions, I think that's a good moment. We can have 5 minutes or something. Yes, please come here.
I just wanted to ask if this program, is it like user-friendly? Is it like everyone can type the input and then ask for the output? We can use it as students, or is it something?
Okay. Since we are developing this tool inside our research group, also to answer goals that are changing over time, we are trying to maintain both levels of complexity. So we are using it coding and from command line in a more complex way. But we are also developing, it's already there, a web interface in which you just have to input the few input files, and then you can download the results. And it's a web service, so it's running on a server because behind it there's a lot of computation and mainly simulation. It's very heavy. So it's also to avoid the user to use their laptop that cannot maybe be sufficient power, to do this analysis. So, and maybe on May 19, maybe we can try in the class to use it.
Yes. So roughly speaking, the user interface is done by an Energy Plus IDF, a first IDF. We do not have integrated a CAD solution because they exist, okay? From Design Builder to Open Studio to OnAB, okay? So that's it. And after there is a simple file that manages all of the requests, and the IDF will be completely rewritten by the tool itself. You don't see it, okay? And also this type of input file that may look not so easy at the beginning. In reality, you don't need to code anything, okay? There is a manual for that. Is already built in a way that can be without so many difficulties in future, be, I don't know, integrable with scripts or graphical elements like Grasshopper tools or things like that, because it's already conceived to produce a pre-filled list of variable and requests. And the file, the weather file, if you do not have a direct connected weather station or services, that's also, yes, that's also one of the reasons. We have a lot of pre-built scenario because you may need also the connection with sensor in some cases for real-time analysis of performance gap, while in other cases, like sensitivity analysis for design, you don't need it because you don't need to have the monitored data for that. Other question? Someone on climate correlation? I have one for May. How complex will be at the beginning to build? Because now we have understood when you have the correlation, you don't need to recalculate it. So roughly speaking, having the correlation equation, you can input it in a control system. But how complex will be to build a new correlation list of equation for a new site, for example, or for a new building in a site? And that's the first part. And the second part is, do you plan to test it, no, in a real building?
Yes.
Okay, that's the question. Thank you.
Yes, for the first question, for the new building, to get a more accurate result, we need to define the very relevant boundary condition. Let's say, if we want to predict for the office environment, what kind of the office site we need to define, because it really affect, for those internet heat gain or the site of the office, it will be affect. So we need to define the very relevant boundary condition. But for the residential building, some of the units are quite typical at some point. So we have to develop the different unit layout. Let's say the unit layout for the east orientation or west orientation, those things we need to define. So in this case, some of the boundary condition we can use a general model for the, whatever the building is in one city, or let's say the window opening, some of the unit may have the very small window, or some may have the very big window. So in this case, the boundary condition will be different. So according to the relevant boundary condition, we need to select what is the most, appropriate, reference model for the user to use for the prediction. So it has some limitation or some dependency on the prediction equation for the user to use. And then the rest, the other occupant activity or all those information is quite flexible because there is the focus data. We just need to put it in our Excel spreadsheet. So I hope I answer your first question. And for the second question, currently we are working for the demonstrating, package for the PRELUDE. So currently, in my presentation, I was showing that the Krakow office and the 80 apartment. So that is currently in the demonstrating building we are testing. And in future, hopefully for the summertime, we can test it for the living lab in Australia for the summer operation season. So that is the future plan for the testing. Yeah.
Thank you. So thank you to all. Thank you to be there, especially for the speaker and also for all people that has listened and asked things. And we will see next time, potentially 2nd of May, and we will confirm, of course, through our site for the next event. So thank you very much.